So, hereby I open the public defense by Tim Augustin of his Ph.D. thesis entitled Enhanced Active Resonant DC Circuit Breakers for HVDC Grids. The respondent here is Tim Augustin, who is a doctoral student at KTH. He has conducted his research at KTH under the main supervision of Professor Hans-Peter Nee. Yeah, somehow. And co-supervisor, Associate Professor Marley Becerra has been, and also Associate Professor Staffan Norga has been co-supervising, I think, roughly the first half of the research. I would like to give a special welcome to our faculty opponent, Professor Jörgen Bieler from ETH in Zurich. Welcome.
Welcome.
And the thesis will be evaluated by the grading committee. So I would like to give a warm hand to the welcome committee. And I take it in the order of geographical distance. So first of all, I would like to welcome Professor René Smits from Jiao Tong University. Welcome, René.
Thank you. I'm here.
And then we have Professor Elena Lomonova from Eindhoven University of Technology. Welcome.
Thank you very much. I'm here.
And then finally, we have Professor Torbjörn. Sorry for the spelling, Torbjörn.
No problem. It's always misspelled.
From the Chalmers Tekniska Högskola in Sweden. Then I will also introduce the stand-ins we have for the grading committee. We have Professor Emeritus Göran Engdahl on the line, and he's stand-in for the grading committee. However, it looks like we have a full grading committee and it works perfect. So hopefully we'll not be needed to take your service into action. And the same, we have Associate Professor Nathaniel Taylor as stand-in also. You are also welcome, of course, to this public defense.
Hi.
So, the procedure of this public defense is as follows. First, I will give the opportunity to the respondent to give any remarks on if he has found some formal errors in his thesis. And after that, I will ask him to present his thesis. That will be followed by the review of the work by the opponent, Professor Jörgen Bieler. And when he declares it's completed, the review, I will give the word to the grading committee so that they can put their questions and the remarks that they want to do on your thesis. Then finally, I will invite the audience to put questions and give remarks also, and you can do it over the Q&A session in the webinar. And you can also send a chat message to me and I can make you so that you can speak out your question if you would like to do that from the audience. And then I finally close this public defense, and the grading committee will meet in another Zoom room to find whether they want to pass or fail the respondent. So, Tim, do you have any errors that you would like to draw our attention to?
No, I don't.
All right. In that case, I give the screen to you.
And thanks, Mark, for the introduction. Welcome also from my side, and thank you for attending my defense. So, as the title of the thesis suggests, we have dealt with the enhanced active resonant DC circuit breakers as part of our research activities. And in this thesis, they are discussed in the context of HVDC grids. The enhanced active resonant DC circuit breakers are a novel type of DC circuit breaker we have conceived as part of our research activities. And in the presentation, I'm going to start to explain them backwards. So I will start with explaining why HVDC grids, then I continue with why DC circuit breakers are needed in HVDC grids, and then I will also explain you the enhanced active resonant DC circuit breakers and also some experimental results from the laboratory. Why HVDC grids? Conventionally, HVDC has been used to integrate remote energy sources via long-distance connections, for instance, hydropower plants. HVDC has also been used in point-to-point connection for subsea power transmission. The thing is that more renewables are integrated into the electricity infrastructure nowadays, but the electricity infrastructure was not made for this kind of distributed energy sources. Therefore, eventually the grid has to be expanded. in the future energy mix, solar and wind will have a major share. And the thing about solar and wind in particular is that they're intermittent by nature. And this intermittency is also challenging for the existing electricity infrastructure. HVDC grids could be beneficial in this regard because it is possible with the HVDC grid to transfer power between various regions and even out the fluctuations. HVDC grids could also interconnect and connect the offshore wind farms to the main shore, and hence HVDC grid could be the key enabler for a greener energy electricity supply. The thing is, as in every power system, faults can also appear in an HVDC system. In an HVDC system, the faults can appear on the AC side or on the DC side, and the handling of DC faults is particularly challenging. In this picture, you can see a point-to-point HVDC link consisting of two converters. These two converters are interlinked by a transmission line. Let's say a DC fault appears right on the DC link. Conventionally, one would handle this kind of DC fault by opening the AC circuit breakers of the converters. In this case, the DC fault is isolated from the AC side. This is a rather slow process. Another possibility that has been used is to use the converters to actually control the fault current on the DC side throughout the fault. The thing is that this requires converters that still have control under a DC fault. The converter that is expected to be used in HVDC grids, however, does not have this capability. Another option are DC circuit breakers, which are now included on the DC line. DC circuit breakers are typically not used because they are quite complicated and expensive. Let's say this point-to-point link is expanded into a radial grid configuration. If one would now apply the first option for fault handling, one would also need to open the AC circuit breaker of this third converter. This means that the power flow on this healthy line is also interrupted, and hence this leads to unnecessary power outages. If the grid is further expanded, and therefore these AC circuit breakers are not really an option if the one has a grid. If the grid is further expanded into a ring configuration, the power level of the grid also increases. At some point, the grid becomes really large. And if one would use option 2, this would entail that the DC voltage of the whole HVDC grid is ramped down, and hence the power outages would also be very high and potentially unacceptable. If the grid is further expanded to, for instance, with a mesh configuration, option 2 really is unacceptable, and the only option are DC circuit breakers. And this is why we have considered them in our research. One question is, what's the deal with DC circuit breakers in the first place? Why are they so complicated? In an AC system, the fault current has a natural current zero crossing. The AC circuit breaker consists of two contacts that are opened, drawing an arc. The contacts open and the arc keeps on burning. At some point, the natural current zero crossing occurs and the arc in the circuit breaker extinguishes. The AC circuit breaker then has isolated the AC fault. In the DC system, however, the fault current never crosses zero naturally. Here you can see an exemplary fault current for a DC system. As you can see, the current more or less increases unto some steady state value. If one would apply the AC circuit breaker on the DC side to handle such faults, the arc would never extinguish because of the lack of the current zero crossing. Therefore, specialized DC circuit breakers have to be used. Down here you can see a simple DC circuit consisting of a DC source and a DC circuit breaker. In order to interrupt the current flow, the DC circuit breaker must insert a counter voltage that exceeds the DC source voltage. Two practical implementations are possible. Okay, got your attention?
Yes, now
this was not for such a long time, but now I should be back. Okay, But anyway, maybe I would just repeat this. So this simple DC circuit, it has a DC source and a DC circuit breaker. And the DC circuit breaker has to insert a counter voltage that exceeds the DC source voltage in order to interrupt the current flow. Two practical implementations are possible. One would be a typical AC circuit breaker that has an arc voltage that is so high such that it exceeds the DC source voltage. This is, however, not feasible for HVDC applications. Another option is to use a pure semiconductor-based solid-state breaker. For an HVDC system, hundreds of power semiconductors would need to be connected in series, and the semiconductors would then turn off the fault current. The thing is that these power semiconductors would also exhibit losses during normal operation, which would be unacceptably high. Therefore, a workaround is needed. This is the general DCCB structure, which you can see in this illustration. The general DCCB structure consists of three paths: the main path, the commutation path, and the energy absorption path. In normal operation, the main path conducts. It should have a very low impedance and hence very low losses. If the DC circuit breaker is tripped, the current is commutated from the main path to the commutation path. Depending on the implementation, the delay of this stage will vary. After some time, the current is then commutated from the commutation path to the energy absorption path. The energy absorption path is responsible for inserting a counter voltage that drives the fault current to zero. This interrupts the current flow. The energy absorption path is typically implemented with metal oxide varistors, MOVs. An interesting aspect is that the DC circuit breaker current and voltages, as seen as from the terminals of the DCCV, have a characteristic shape. You can see this in this plot. The triangular shape corresponds to the current, and the dashed lines correspond to the respective inserted counter voltage. As you can see, the shape is very similar in both cases. The only thing differs is when the counter voltage is inserted. And this is caused by a concept-dependent internal commutation delay. The main source for delay of a DC circuit breaker is the mechanical switch. Every practically relevant DC circuit breaker uses a mechanical switch in the main path to guarantee low losses. However, mechanical switches open much slower than it is, for instance, possible to switch a semiconductor, and hence it is not possible to avoid such delays. Considering that the structure of the general DCCB is more complicated than an AC circuit breaker, it can also offer functionality in addition to interruption. An example is the auto reclosing operation. In a system that uses overhead lines, faults may be of temporary nature. For instance, if a tree just touches an overhead line momentarily. The circuit breaker can then reclose and normal operation is resumed. Reclosing can be done by first reclosing the main path and then resuming normal operation, or alternatively by reclosing with the commutation path and commutating the current back to the main path for normal operation. Another aspect is bidirectionality. DC circuit breakers can be both unidirectional and bidirectional. A unidirectional DC circuit breaker can only interrupt in the normal current direction, whereas a bidirectional DC circuit breaker can also interrupt in the reverse direction. An interesting capability is the proactive commutation mode. In this case, the DC circuit breaker commutates the current to the commutation path before the DCCB is tripped, already when it internally determines that this could be a critical condition. If the DCCB is then tripped at the later point, the delays of this protection delay can be compensated, which then speeds up the interruption process. However, it could turn out that the DCCB is never tripped, and then the DC circuit breaker must at some point decide that this was not a fault, and it has to commutate the current back to the main path to resume normal operation. Another interesting functionality is fault current limitation. To implement fault current limitation, the general DCCB structure must be modularized. In this illustration, you can see a general DCCV structure with modularized commutation and energy absorption path. Both the commutation path and the energy absorption path consist of two modules. One module in the commutation path is connected in parallel to one module in the energy absorption path, respectively. Let's have a look at the state where the commutation path already conducts. It is now possible to operate these modules independently of each other. If, for instance, the second module in the commutation path is turned off, the current will commutate to the parallel connected module in the energy absorption path. Now only one module in the energy absorption path is inserted, and this means that the inserted counter voltage is also reduced. If even more modules are added, for instance 4, 8 or whatever, it is possible to stepwise increase the counter voltage and to limit the fault current or even control it. A multitude of DCCB implementations has been proposed in the literature. Most of these can be categorized as current injection DCCBs or hybrid DCCBs. The main component of a current injection DCCB is a typical AC circuit breaker in the main path. The injection circuit is then used to create an artificial current zero crossing in the main path to extinguish the arc in the AC circuit breaker. The hybrid DCCB, on the other hand, uses power semiconductors to operate. The main path consists of an ultra-fast disconnector switch and an LCS, load commutation switch. This is a power semiconductor rated for only a fraction of the line voltage. The commutation path also consists of power semiconductors. This is now a high voltage power semiconductor valve, which means that hundreds of power semiconductors are connected in series. Thus, the commutation path is somewhat like a solid state breaker. The current is then commutated from the main path to the commutation path by turning off the LCS and turning on the semiconductors in the commutation path. The semiconductors in the commutation path then turn off to interrupt the current flow. Both concepts use a metal oxide varistor in the energy absorption path, which is quite typical, as I mentioned before. The thing about the hybrid DCCB is that the power semiconductors add a considerable advantage, which is flexibility, since they can be switched easily. And the thing is, though, that these power semiconductors are underutilized in this application. You have to consider that faults should ideally never occur. And the power semiconductors are made to be switched at a switching frequency as done in power electronic converters. Hence, in this application where they only have to operate seldom, they are grossly underutilized. The thing is that these power semiconductors are very expensive, which is quite a stark contrast that the underutilized component actually contributes most to the cost. The goal of this research was now to merge the current injection DCCB structure and the hybrid DCCB structure into one concept and to combine the advantages of both. This is done by getting rid of the power semiconductors in the commutation path. We have considered to replace these power semiconductors with tubes. In the laboratory prototype, we implement this with a triggered vacuum gap, which you can see in this illustration. The triggered vacuum gap consists of two main electrodes. This is the anode, and this is the cathode. The triggered vacuum gap also has a third electrode, which is the triggering electrode. In order to turn on the triggered vacuum gap, a high voltage pulse is applied to the triggering electrode, which initiates a breakdown between the triggering electrode and the cathode. And here there's some current flow. If a minimum voltage is now present between the anode and cathode, the main gap would also exhibit a dielectric breakdown, and there will be a current flow from anode to cathode. In this state, the triggered vacuum gap is turned on, and it behaves similar to a thyristor, which means that it will only turn off if its current drops below a certain level, which is relatively low, almost zero. The advantage of triggered vacuum gaps are that the structure is very simple, and these are also very cheap devices. Triggered vacuum gaps are also robust and reliable. Here you can see the picture of the triggered vacuum gap used in the laboratory prototype on the left-hand side. Next to it, you can see the thyristor part of an IGCT. The triggered vacuum gap is rated for 25 kilovolts, whereas the IGCT is rated for 4.5 kilovolts. This demonstrates how compact these triggered vacuum gaps actually are compared to power semiconductors. In this table, you can see the ratings of triggered vacuum gaps from the manufacturer we purchased from. We used this unit in our laboratory prototype. As you can see, it has a quite substantial current rating of 200 kiloamps. The thing is that even larger devices are available, as for instance, this RVU63, which is available for a voltage of 55 kilovolts, and also a current of 700 kiloamps. A key rating of the triggered vacuum gap, though, is the maximum charge capability. This maximum charge capability limits the conduction time of the triggered vacuum gaps. Nonetheless, they can still conduct for a very long time. And then, because of these high power ratings, they are an ideal candidate for HVDC circuit breaker applications. And also, considering the high voltages, the number of series connected components in the commutation path is reduced. Another plus of the triggered vacuum gap in particular is the minimum voltage required, which is very low compared to other similar switches. A practical aspect is that no cooling system is needed. The disadvantage is that the characteristics of the triggered vacuum gap in DC circuit breaker applications are still unknown. Only few manufacturers sell such triggered vacuum gaps nowadays. This is because triggered vacuum gaps are only used in niche applications. However, they are so simple so that manufacturing could be increased at any time if there should be a sufficient demand. Let's now have a look at the enhanced active resonant DC circuit breakers. On the left-hand side, you can see the originally proposed configuration. As you can see, the main path is similar to the hybrid DCCB. Here you can see the triggered vacuum gap in the commutation path. An RC circuit is connected to the anode of the triggered vacuum gap to provide a high voltage potential that is needed for the triggered vacuum gap to operate, to satisfy the minimum voltage requirement. The RC circuit is pre-charged from the DC line through this diode. The injection circuit in the commutation path is needed to extinguish the discharge in the triggered vacuum gap with an artificial zero crossing. This is similar to a current injection DCCV. During our research in the later stages, we found out that it is possible to simplify this configuration under certain circumstances. To do this, the minimum voltage requirement of the commutation path has to be created internally. And in this case, the LCS is used for this purpose, in a process that we named LCS-assisted triggering. Now let's have a look at some more aspects of the laboratory prototype. As I mentioned to you before, every DCCB needs a mechanical switch. In the laboratory prototype, we used a vacuum interrupter. Here you can see this vacuum interrupter, and it is mounted on top of a Thompson coil actuator. The Thompson coil actuator is an electromagnetic actuator which can rapidly open and close mechanical switches. To operate this Thompson coil actuator, a complex system is needed, consisting of the control panel, the capacitor bank as energy source, and a TC driver. Here you can see the inside of the control panel. It houses various electronic components needed to control the actuator and to energize its coils. On the left-hand side, you can see an illustration of the Thompson coil actuator. It has two coils, an opening coil and a closing coil, and a metallic armature between it. If the opening coil is energized, the armature is pushed towards the closing coil. For a closing operation, the procedure is the other way around. We have tested this in the lab, and here I have a recording from the high-speed camera, and in this case, this is the open, close, open operation of the actuator as needed for auto reclosing operation. As you can see, the armature moves down. Then after some time, the armature moves up again for reclosing. It immediately reopens again to finish this open, close, open sequence, and it worked without any problems. However, I have to mention that a substantial amount of energy is needed to make this Thompson coil actuator work. I mentioned to you that the DCCB is able to provide functionality in addition to interruption. To test this kind of special capabilities, an advanced test circuit is needed. Here you can see the test circuit that we proposed for this purpose. And here you can see a photograph of the laboratory prototype. This is the mechanical switch that I already described. And the structure right here is the test circuit. The DCCB is integrated in the structure of the test circuit for practical reasons. The other stuff is just measurement devices and cables. The topology of the test circuit allows to implement various test scenarios. Here you can see an exemplary test scenario on the right-hand side, where the fault current first increases in the test unto the trip level. At this point, the DC circuit breaker interrupts and the fault test current reduces to 0. After some time, the DC circuit breaker recloses. The test current starts to increase again, but it does not increase to the trip level. Because of this, the DC circuit breaker does not need to interrupt, and instead the test current reduces to the normal operation level again. This allows to evaluate whether the DC circuit breaker can abort the proactive commutation operation after a previous interruption attempt. Now I want to come to the experimental results. These are mainly taken from publication 7, which is our latest publication. Publication 5 was more or less a pre-study. Here you can see our first test, which was the triggering of the triggered vacuum gap. And this is done for the originally proposed configuration. Initially, the RC circuit is pre-charged from the DC line. The DC sources were then separated from the DC circuit breaker to prohibit that the triggered vacuum gap interacts with the DC sources during this test. The triggered vacuum gap was then manually triggered. We have conducted various experiments at low and high current levels, low and high voltages, and we found that the triggering process is very reliable, and actually we have never seen any mistriggering at all. The thing is that for this kind of operation of the triggered vacuum gap, low voltages are kind of a restriction because of the minimum voltage requirement, and the same goes for low current. Therefore, we have also put considerable amount into studying at this kind of current levels. On the left-hand side, you can see the results from the triggering test for 2 resistor values, a lower resistor value and a higher resistor value. This resistor corresponds to the resistor in the RC circuit. The depicted curves are the measured voltage across the triggered vacuum gap. We have taken several measurements for each resistor. As you can see, the curves differ between experiment to experiment. This just demonstrates how stochastic the behavior of the arc discharge inside of the triggered vacuum gap are. Another aspect is that it is possible that high amplitude oscillations occur in the discharge voltage. The thing is that these kind of oscillations and the volatility of the discharge increase at lower current levels. This you can see for the higher resistor value, where the oscillations can be basically observed at any time, and they also always occurred. The thing is, though, that the device still triggered successfully. However, the oscillation can cause the discharge to extinguish prematurely. In the next step, we studied the commutation from the main path to the commutation path. Here in the first slide for the original configuration. In the initial state, the main path of the EAR DCCB conducts. This you can see with the blue current in the beginning, which corresponds to the LCS current. Then the triggered vacuum gap is triggered. This causes the RC circuit to discharge into the triggered vacuum gap, which gives this RC-like current in the triggered vacuum gap, which is the red line. And after a delay, the LCS is turned off to commutate from the main path to the commutation path. And this happens right here. And this is a very fast process, and it is also a very reliable process. We have even tried to change the delay of this commutation where the LCS is turned off, and we found that it essentially does not affect the success of the commutation process. It is quite the contrary. It was even possible to commutate in this highly oscillatory initial phase. The thing is, though, that there is the chance of a discharge instability. The green curve, which is depicted in these graphs, corresponds to the measured voltage across the triggered vacuum gap. As you can see, at this low current level, the discharge voltage is relatively volatile for both resistor values. But in case of the lower resistor, there is a discharge instability, which leads the discharge to extinguish. The DC circuit breaker interrupts at this point. However, it was not supposed to interrupt, so this is undesirable. We think that this happens because discharge in the triggered vacuum gap starts interacting with the RC circuit, but only if the resistor value is relatively low. By carefully dimensioning the RC circuit, the instability can be avoided, as you can see for the higher resistor value. If the current level is increased, the instability completely disappears, since also the volatility of the discharge reduces. In the next step, we analyze the simplified configuration. In this state, the main path conducts. In the next step, the LCS is turned off. The snubber of the LCS starts to conduct, and it forms the turn-off voltage of the LCS. In this state, the ultra-fast disconnector or mechanic key switch is still in its closed state. This means that the voltage of the snubber also appears across the terminals of the triggered vacuum gap. The voltage measured across the triggered vacuum gap corresponds to the green line here. The blue line is the current in the LCS, and the red line, the current in the triggered vacuum gap. When the snubber voltage and hence the triggered vacuum gap voltage increases beyond some level, which exceeds the minimum voltage requirement, the triggered vacuum gap can be triggered. You can now see substantial oscillations in the arc voltage. Nonetheless, not even within 1 microsecond, the current commutates from the main path to the commutation path and hence the triggered vacuum gap. And we found that this is a very reliable commutation process. In fact, it never exhibited these kind of instabilities we observed for the originally proposed configuration. We have also tested this at various current levels, and it was equally reliable at all current levels. The thing is, though, that the turn-off voltage of the snubber depends on the current level. This means at a lower current level, the turn-off voltage of the snubber increases more slowly. Therefore, the delay between turning off the LCS and triggering the triggered vacuum gap has to be adjusted. Here you can see this for various current levels. For instance, for this 20 amp level, the triggering delay is approximately 2 microseconds more than for the higher current levels. In a practical DCCB application, it would be required to have some kind of monitoring system that adjusts the triggering online. The main purpose of the DCCB is, of course, interruption, and we tested this as well. On this slide, you can see some results for the originally proposed configuration and the simplified configuration. Down here, you can see the originally proposed configuration and the simplified configuration in the state where the commutation path already conducts. since we have discussed the other commutation process to the triggered vacuum gap on the previous slides. The turn-off process and the interruption process are very similar for both configurations, and here I will only explain it for the originally proposed configuration. In this state, the triggered vacuum gap conducts, which you can see with this blue line here. And it conducts for a while until the current in the DCCB exceeds the trip level. At this point, the injection circuit is activated. The implementation for the injection circuit we use in the lab first causes current pulse in the opposite direction, and then a second current pulse in the correct direction, which then causes the artificial current zero crossing in the triggered vacuum gap, and hence gets rid of the discharge and turns it off. In the next state, the fault current recharges the RC circuit and the energy storage of the injection circuit. The injection circuit voltage starts to increase. At some point, it is so high that the voltage also on the MOV causes it to become conductive because of its nonlinear properties. This is this counter voltage that is inserted by the MOV in this state, which then also interrupts the current flow. We have tested this process from low currents up to high currents of 1.2 kiloamp, as illustrated here for the simplified configuration. And we have not observed any limitation in the interruption process for the tested current levels. We have also tested the proactive commutation mode. Here you can see both configurations where the main commutation path and hence the triggered vacuum gap already conduct. On the left-hand side, you can see the experimental results. The test current increases, but not until the trip level. Hence, the enhanced active resonant DC circuit breaker does not have to interrupt. Instead, the test current drops again to the normal operation level. And after some while, the control system of the EAR DCCB has to decide that this has been long enough for the triggered vacuum gap to conduct, and now it should abort proactive commutation. At this point, the mechanical switch is reclosed, and then the LCS is turned on. This immediately commutates the current from the triggered vacuum gap to the main path, because the arc voltage of the triggered vacuum gap is considerably higher than the turn-on voltage of the main path. So we found that proactive commutation works without any problems. We also evaluated the auto reclosing capability. On the left-hand side, you can see the results for auto reclosing operation with the triggered vacuum gap. This first current pulse here corresponds to the first interruption attempt, which is successful, and this process I already described on the previous slide. After approximately 1 second, reclosing is started and the triggered vacuum gap starts to conduct immediately. When the current surpasses the trip level, the injection circuit is again activated to turn off the discharge in the triggered vacuum gap. And we found that this kind of reclosing operation was also reliable. The thing is, though, as you saw, that reclosing could be attempted after 1 second. This is quite long for practical applications, but the triggering unit that was sold with the triggered vacuum gap could only be operated once per second. So this was a limitation. Therefore, we have investigated an alternative reclosing strategy based on the mechanical switch, which you can see here on the right-hand graph. The reclosing here already takes place after 300 milliseconds. The dashed line now corresponds to the current in the mechanical switch. As you can see, the triggered vacuum gap is actually never operated in this case, and the mechanical switch conducts the current all the time. The mechanical switch is now also operated not as a disconnector, but as an arcing switch, so it is operated with an arc. At this point, the test current exceeds the trip level, and now the circuit breaker should operate. However, this is the time when the mechanical switch starts to open. After some time, the mechanical switch can take the transient recovery voltage, and that's when the injection circuit is activated to now extinguish the arc in the mechanical switch, similar to as it was done for the triggered vacuum gap before. As you can see, the second current pulse is higher than the first one. And that's because in this kind of reclosing strategy, one cannot utilize proactive commutation. But this also works reliably. The advantage of using an arcing mechanical switch is that it provides redundancy. In case there is some problem with the triggered vacuum gap, it is still possible to operate the enhanced active resonance circuit breaker similar to a conventional current injection circuit breaker. Now let's have an overview of the EAR DCCBs. We have proposed various configurations of the EAR DCCBs, both the unidirectional and bidirectional configurations. We have proposed symmetric and asymmetric bidirectional configuration. Asymmetric means that the interruption capability of the configuration is not the same in both current directions. This can considerably reduce the component count and hence also the costs. We have also found that the EAR DCCBs can be simplified if an LCS is used. The simplified configuration decouples the internal commutation process from whatever is going on at the terminals of the DCCB, and this improves the reliability of the EAR DCCBs. We have also shown that with this simplified configuration, it is possible to modularize the DCCB configuration more easily, which then facilitates fault current limitation. Another aspect is that the simplified configuration is also compatible with more injection circuits, which is beneficial, of course. A general advantage of the EAR DCCB is that it separates the main path from the interruption medium in contrast to current injection DCCBs. This means that the mechanical switch in the main path never has to operate at relatively high current ratings like 9 kiloamp. This allows to use smaller mechanical switches, which can potentially be operated faster or with a simpler actuator. And as I told you, the mechanical switch is always the true bottleneck. Lastly, I would like to summarize. HVDC grids require DC circuit breakers. There are many DCCBs, but all of these resemble the general DCCB structure. The thing is that how the general DCCB structure is implemented only affects internal commutation delays. As seen from the terminals, the characteristic current, shapes, and voltages can be observed. The major bottleneck and main source of delay is always the mechanical switch, and this cannot be avoided in HVDC applications. Hybrid DCCBs are very flexible DCCBs, and they can offer more functionality compared to current injection DCCBs. This is because they use power semiconductors, but the power semiconductors are very expensive. The EAR DCCBs replace the power semiconductors with triggered vacuum gaps. Triggered vacuum gaps are high power devices, which are also cheap, reliable, and compact. Despite of these clear advantages, the enhanced active resonant DC circuit breakers operate similarly to hybrid DC circuit breakers. The operation of the enhanced active resonant DC circuit breakers was demonstrated with experiments in the laboratory. In addition to interruption tests, we have also shown that the enhanced active resonant DC circuit breakers can handle proactive commutation and auto reclosing. So now I'm at the end of my presentation. I have to say that this was a lot of work, but it was also a lot of fun to do this work and to get all these kind of results. And I must say that I may have not expected to actually get all of these things working when I started my PhD. By saying this, I would like to conclude and thank you for your attention.
Thank you very much. Thank you very much for the much covering presentation of your work. All right, now it's time to scrutinize and review the work of Tim Augustin. I'm very happy to welcome Professor Jürgen Bieler. to do the discussion and the scrutinizing of his work. So welcome on the screen, Jürgen.
So welcome also from my side. I don't see who is present, but yeah, also thank you for inviting me to be the opponent here in the review process. Was quite interesting to read your thesis. I think you covered quite a wide range of topics, starting from Thompson coil design, simulation of topology invention, simulation grid level. So quite a wide range what you covered there. So I think it's quite impressive. Maybe starting a bit with the questions, yeah, from the presentations, going maybe to the slides. Don't know if you can maybe open them again. Would be easy, maybe also for the audience, if we discuss on something, they could be maybe follow this a bit. Yeah, maybe just starting from the end a bit. Slide 20 maybe you had there with this. We had this commutation loop. Yeah, so I think you showed that the commutation here is quite fast, and that's all designed for your test setup, as far as I understood. Could you comment a bit on the leakage inductance, what you have in the loop there? What is the voltage for driving this leakage inductance, and how this would scale up then to a full system? Because that's all a bit scaled down quite a lot. And in the HVDC system, I think the distances and all the things, it's larger. So how do you see this, how this would scale up then?
First of all, I must say that the arc voltage of triggered vacuum gaps is relatively low because of the vacuum arc. So it's also kind of like a worst case. And in the laboratory prototype, this is not, I would say, it is built with bus bars and so on, but it is not optimized to get the lowest leakage inductance possible. So I have not quantitatively evaluated what is the value. So I cannot comment on that because it was not optimized for this purpose. And I think that in general, one can say that the leakage inductance, it will only affect the speed of the commutation process, but it is not critical for the success. And we were sort of, for us, we did not analyze it in depth because this was not the main focus of our study.
Okay, but how big is the driving voltage what you have in your system for commutation?
So the vacuum arc voltage is like typical between 10 to 20 volts, let's say. So it's relatively low. And then there's, of course, also in the original configuration, a voltage drop across the diode.
Yeah, yeah. And how would this scale then up to a full system? If you go for a HVDC, then the distances become much larger, the leakage inductance becomes larger. So what do you think the commutation takes then? Much longer then, or what do you estimate?
I mean, I don't want to give any vague answer since I did not calculate it or anything, but I would say that if one, for instance, would stay with this particular triggered vacuum gap, because this is highly dependent on what uses for this discharge closing switch, as I called it in publication 5. And for this triggered vacuum gap, one could use one triggered vacuum gap, for instance, for a module of 40 kilovolts. And then the process will sort of be similar for scaling it up. And the arc voltages of all the modules would, yes, add up by the number of connected modules. But let's say as part of the experiments, because of practical reasons, we use the triggered vacuum gap. If you would use a different triggered spark gap, for instance, with SF6 or whatever, the arc voltage could also be increased. So this would then, of course, speed up the commutation process. So there are many design parameters which affect this and which can also make it faster at HVDC. Yes, I hope this was somewhat an answer.
Yeah. that's also because what you triggered vacuum gap, what you've shown, you have also shown two examples for this, what you could buy, and the voltage is quite limited. So at higher voltage or HVDC voltage, you would need to connect quite a few of them in series to be able to operate the system in the end. Do you know if there are vacuum gaps with higher voltages also available? Or that's the limit what you have shown. So I think it was 50 or 60 kilovolt.
This is from the manufacturer we purchased from. So this is up to my knowledge what they offer, but I think they are also quite active in research activities. And when one looks at their papers, I think they also have shown some switches for even higher voltage. And that being said, let's say the thing is in vacuum, we often talk about vacuum interrupters, the mechanical switch. And these are used in medium voltage applications because of the non-linearity of the dielectric capability. But for this kind of arrangement, the non-linearity is not such a hurdle since there is no mechanical movement. So one could just move the electrodes further apart. The only downside of this would be that a higher triggering voltage would be needed to cause this initial discharge in the triggered vacuum gap.
So this would make then the triggering process, what you've shown, is already unstable. For your setup, would it make it even more unstable and more oscillations would then occur?
I mean, it's somewhat speculative, but it could be. But on the other hand, yes, I would say this would require further research. Since this device is, it could be built, but we have not built it.
Yeah. Because you also discussed in some place in your thesis different types of for you this DCS, how you call it. You have chosen now this vacuum triggered gap here, but there are others. Why did you choose this vacuum triggered gap here? Was there a special reason for that?
Maybe I can just also show it if we're discussing so that everybody knows what we are talking about.
Yeah, for sure. Yeah.
So here we have it with all bullet points already shown. So one key point is, of course, availability, because we, when we have so many activities, we cannot start designing our own triggered vacuum gap or other kind of discharge closing switch. So it should be possible to purchase it relatively fast. This was one aspect. And then another aspect was also the cooling system, because I know from a previous PhD project, they once had a problem with a cooling system, which broke because the pipes, I think, froze in the winter. And I did not want to have such a possibility. I wanted to keep it simple. So this was also a main argument. And we have also evaluated the other DCS switches that are named in publication 5. And there are also some that are available, for instance, the Ignitron that is named in this paper. But this would have required, I think, even a double jacket cooling system. So this was one of the main aspects. From the ratings, at these kind of levels we tested in the lab, we would have never really gotten to the limits.
Okay, but why you didn't choose, for example, a simple spark gap or something like this, which you could also buy off the shelf? Why vacuum gap?
I mean, there are also, I mean, let's say you would have just had a triggered vacuum, triggered spark gap in air without any kind of pressure chamber. Then the thing is that it can be expected that the DIDT and DVTT capability of this device is lower, or so to say, the dielectric withstand capability after the current zero is better of the triggered vacuum gap. This is, of course, something we have not analyzed in experiments, but this is something that we expected. And therefore, we thought that this triggered vacuum gap, because of its superior dielectric property, is an ideal candidate for this application. And this also goes hand in hand with what is written in the thesis about the implementation of this injection circuit. Because as you know, it is a resonant type of circuit, and the higher you can push the frequency, the lower the components values get, and the more, the less bulky it is, and you can also save money. I mean, this capacitor that is needed in the injection circuit, it is also quite substantial.
Okay. And where do you see then the limit of the frequency, what you said? What is the limit of this oscillation frequency then?
I think I would try to avoid this question by saying that I've drawn this injection circuit on purpose as it is in a general way, because this, I think the frequency limitation is heavily dependent on how the injection circuit is realized. And for instance, this one here, it's compatible with basically all injection circuits. And then there are some type of injection circuits that build up the injection current successively with oscillations. And by doing this, the current is gradually ramped up to the interruption level. This means that then at this, that the voltage and the current of the injection circuit are ideally suited to the current level, which reduces the dIdt and dVdt requirements. So this is, if I can, as a concrete example, for instance, the Cybrake implementation.
I think that the one important aspect is that you have to limit this di by dt or the dv by dt after the breaking, then that you get not a triggering of the gap then in the end. So that I would see then as a main limitation for the frequency of the injection circuit, because you have the sinus, and if you get the di by dt and the dv by dt, and that's limiting then the.
Yes, but the thing is that in this implementation that Cybrake has, the current is always ramped up, so it will be sort of ideal. The current, the dIdt is relatively low always because the current is gradually ramped up. And also I would say there's another limitation in such implementation, which could be the switching frequency inside the injection circuit of the other components, not only the resonant components. So this has also to be kept in mind, since if you have an IGBT of a substantial power rating, you have some limitation there. You cannot make it, let's say, 100 kilohertz.
Yeah, yeah. When we see now the full schematic of the DCCB, you have the schematic there. So what is missing to make such a system working in a real environment? You mentioned monitoring at some point. So what would you need to measure, control, auxiliary power supplies in such a system? So just to make it such the picture here on the right hand side, for example, to make it complete.
Yes, I mean, there are many auxiliary components needed. And for instance, this injection circuit needs an auxiliary power supply to pre-charge its capacitors. There are also some solutions that are arranged in such a fashion that the injection circuit is pre-charged from the DC line. But then there are also, again, most likely some mechanical switches to reconfigure the injection circuit to allow a path to ground. And the triggered vacuum gap, of course, has a triggering unit, which also has to be energized. An option in this case, though, could be if one, for instance, uses a discharge closing switch with laser triggering, then one only has to supply the laser and the triggering unit is galvanically isolated. Then, of course, here one needs some gate signal for the IGBT to operate, but then I think it should also be possible to supply an arrangement where the power is transmitted via fiber. And the actuator of the mechanical switch, of course, also requires an energy source, and this needs some DC auxiliary power supplies as well. Because other arrangements, let's say what's done with like spring type of actuators, they could be too slow or exhibit some mechanical delay and so on. And the electromagnetic, they are of course more demanding in this regard.
And what values would you need to measure to make your system operate? You said you need maybe to tune the triggering point in time of the DCS. So you need to monitor certain values in the system. Which ones would these be?
I mean, this is very implementation dependent. But one thing is, of course, that the DCCB has to be aware of the operating current when one wants to utilize this proactive commutation mode. Because then the DC breaker has to decide at this current level we want to, for instance, have a threshold. And the other thing that has to be monitored is the voltage. I guess I have not put too much emphasis on one would have to where one would have to measure if across the triggered vacuum gap or across the LCS, because in this state it is still basically in parallel when the mechanical switch is open. So possibly one could just measure it across the LCS, maybe easier, and then one also could avoid the high voltage in the other operation state.
But in the end, you would measure then the DC current, some voltages, and then you would have a controller which is then adjusting the timing, for example, of the triggering process and stuff like this. So that would be
Yes.
the solution how you implement it. Yeah.
Where was it? This was in the results. This was this graph, you mean? Like this kind of how one would implement this, or?
Exactly. So there you mentioned it explicitly. So triggering, you need to adjust it on the current. So you need to have a kind of a control.
Yes. So one would need to either one could measure the voltage of the snubber, maybe a bit more an extra device one needs for measurement, or one could implement such sort of lookup table where one stores these values, and depending on the current level, then one, for instance, says, okay, let's say the minimum voltage of the triggered vacuum gap is as shown 50 volts, but let's say we just take 500 volts or 1 kilovolt to have some sort of room. And the thing is then that we can look at this table. Let's say we chose this one, and then we look at the voltage, and then we say, okay, for this current level, we should have this delay. For this current level, we have these curves. To get this voltage, we need this delay. Such kind of implementation. And is there something else I have to say? Yes, in the lab, we did it manually. We did not include this in our control system because, let's say, I was a bit distrustful that if there is some noise or so on, that it could disturb the measurement, and then maybe it is set wrong, and then one does not fulfill the minimum voltage, and then maybe the triggered vacuum breaks down. So I was a bit on the cautious side. So this is not something that I've tried in the experiments.
Okay. But this would then further complicate a DC breaker. So besides having more components, you need also some feedback loop in the end, or at least some lookup table, making
Yes.
DC current breaking even more complicated compared to a very simple AC breaking in the end.
Yes,
okay.
But this is a discussion that I also would like to start is if one should really benchmark the DC circuit breakers against AC circuit breakers and what they can do. Since they are so complicated, as I said, one could also utilize their advanced features, which, as I think nowadays, not so many researchers have discussed.
Yeah. Looking maybe the left-hand side, yes, there's also the voltage shown across the DCS. I think in the end we see it with these oscillations. So could you just basically explain what is happening there in this vacuum triggered gap when these oscillations happen? Do you have an idea what is ongoing there?
I mean, this is very difficult to tell, and you also, I have to say that this is the very small time scale here, so it's a couple of microseconds. In the other graph that I included in this publication, it's more or less like 60 to 100 microseconds that are on the x-axis. So that, of course, gives a different picture. And I would say that the thing is that the manufacturer would not completely disclose to me what is happening in the device during this triggering. But the thing is that when the triggering pulse is applied, there is a discharge between the triggering electrode and the cathode. And then there's some sort of plasma. And then when the minimum voltage requirement of the main gap is fulfilled, the whole device exhibits the breakdown. And there's, of course, some transient phase in between that, where the arc is not established, or not even the discharge between the main gap. And this, of course, is a highly volatile process with a lot of things going on. So I think without having a kind of, what is it called, like these kind of chambers where you can monitor the arc discharge, it is difficult or very speculative to say what is really going on inside, especially considering that the electrode structure of this device, this takes a long time, sorry for that. But that the electrode structure of this device it is also not just two electrodes that are apart from each other, but it has these kind of shapes. So I don't know how this influenced the arcing process compared to, for instance, a conventional triggered spark gap.
But there's also a kind of an optimization potential for optimizing such a triggered vacuum gap for your application in the end, or?
Yes, of course, there is a huge potential. And I mean, this is what I also mentioned here, that the characteristics are unknown. This also relates to the DIDT capability. This should all still be tested. And this could possibly be made better for DCCBs, because maybe if one looks at the table, maybe these currents are way too high. Maybe one just needs more charge. So there's a lot of potential to optimize the electrode system for this kind of purpose, and also keeping the DIDT and DVGT capability of this device at current 0 in mind.
Yeah, and looking at the table now, there you see also that the triggering current duration is quite short.
Yes.
You have then the oscillations later. Would it be then helpful to have maybe then a more continuous triggering or repetitive triggering or whatever to make the turn on process more stable?
I think this is something very interesting. One could test it in, or one should test it in the lab. But the thing is that when one has this device in the lab, one also has to be kind of respectful. I mean, it's quite high voltage and it is quite dangerous. You don't know what is going on in the trigger generator, and you ordered it from some foreign country. Then I'm rather on the safe side with what I do with it, to say the least.
Yeah. But that also is then a limitation. What we had shown to us in the end. I think that this re-triggering is only possible after 1 second. You mentioned.
Yes.
This,
but this is because how they implement the triggering circuit. So the thing is that if they, in whatever application that is this device is usually used, which I'm not aware of, to be honest, you may not need to trigger that often. Maybe it's some kind of physics experiments which you run once with a very high current, but then you don't need to re-trigger it. But this company, they have also one paper where they have demonstrated the operation of these devices in, where is it? Sorry, here, this one it was, where they have demonstrated the operation in AC grid applications. And then they had a triggering device optimized for that particular applications. And this one could trigger, I think, either every 10 milliseconds or every 20 milliseconds, something like that. So it's just a design question.
Yeah. As we discussed before, I think there's quite a lot of optimization potential in there for designing such a system for a DC circuit breaker. And as I said, you used something off the shelf, but I think your use case might be a bit special for what the device originally was designed for.
Yes.
Because you're also operating the system at relatively low voltage compared to the design voltage. So you always, or what you investigated mainly, it's the lower limit, not the normal range. So from that point of view, I think, it's a bit special.
Yes.
Okay. I had, one question to the measurement. If you go back, I think 2 slides to slide number 19. One more. Yeah, exactly here. So you have the green curve I. Okay, now we added this. Okay, maybe I've always not seen this in the thesis, but there you have now the absolute value of the current shown, because I was wondering, because it said there's a negative current and it still goes upwards in this green curve. So the first one. Okay. Maybe I've missed this in the thesis.
So
and then there would be one question.
It could be that I've done the plot differently in some instances, because it's easier to see the main current poles if I don't plot the absolute value.
Yeah, okay. But then there's still the question, there is a spike coming at, let's say, 4.8 millisecond. What is happening there in the current?
Yes, this has to be some measurement interference. This has to be noise. I can mention at this point that we also had quite substantial EMI problems in the beginning when we built the test circuit, and then we would always have this kind of EMI, but it would only appear when the arrestor conducts mainly. So, but we actually this was a problem we did not manage to solve entirely in the beginning. And then it did not appear anymore for the enhanced active resonance circuit breakers, because as I explained in the thesis, initially we tested the solid state breaker, and then possibly because of we changed the grounding afterwards a bit, and then it got a bit better. But these spikes sometimes occurred, and this is not related to any thing that is going on in the breaker, in my opinion. And you can also not see that is reflected in any other measurements, even though there's also a small spike here in the arrestor voltage just before it. It could be that there's something that happened.
It's quite surprising because there's nothing dynamically happening in the system at that point of time. So it's a bit surprising that there should be some noise coupled in, which could be by some DI by dt or dE by dt. But at that time, as I said, all is relatively slow there. So it's a bit surprising that there is so late some noise. And I would have expected this more around the switching. So 4.1, 4.2 milliseconds, for example, but not at 4.8 milliseconds. So.
But this was quite, I mean, it was random, so to say. Would not always appear, and sometimes it appeared a bit earlier, a bit later. But I would expect that this is a noise.
Okay. How did you measure the current then in the system? Because you discussed also in one paper the measurement devices, but it was not 100% clear also in terms of voltage measurement what you have finally chosen then.
Yes, I used different devices in the experiments because in some experiments I generally prefer to use Rogowski coils because I was somehow more comfortable with them. But in some experiments, I had to use these kind of Hall effect based sensors from LEM when we measured for an extensive time to avoid that the Rogowski coils saturate. And in this particular measurement, we used the LEM sensors for the current IDC, and in the triggered vacuum gap, TVG. But the pulse current here, this green one, we used with a Rogowski coil from PEM. And the voltage we measured with a differential probe, but I don't recall the manufacturer.
Okay. But yeah.
And then in the current shorter experiments where we did not run into the saturation issue, we always used the Rogowski coils because we found they were not as immune to noise as the LEM sensors. So it could well be that the noise in this experiment was partly also something that was coupled into the LEM sensors.
Yeah. In the end, depending a bit on what noise is, or what's causing the noise issue, I would think that Rogowski coils are typically a bit more noise sensitive for fast transients because they do this integration. And okay, still interesting. Okay, maybe coming to what you have not shown in the presentations so much in detail, to this Thompson coil design, what you also investigated and presented in one paper. Could you explain a bit what you simulated there? Because in the first paper you did a simulation on the Thompson coil. So it was done by FEM. I think, was this a 3D, and how was this arranged? What boundary conditions did you use and stuff like this? Maybe you can explain this a bit.
So you're talking about publication 4, I assume?
Numbering, I have to see it. Thompson coil. Yes, it's 4. Yes, 4.
Because then we had the later publication number 6. That was the one where we tested the prototypes. So 4, exactly. That was a simulational study, and as software we used COMSOL multiphysics, and we used a 2D axisymmetric model. And I have some backup slide where you can see some parts of the model actually. Okay, you just have to, there's some animation here, but here you see the geometry of the model that we used. Here you can see the Thompson coil. It's the upper one for opening and the lower one for closing. And yes, then we solved the Maxwell equations, and these were coupled with a motion, equation of mechanical motion to consider the movement of the armature. And then we had a mesh in between that was changing as the armature moved.
Okay, and you simulated the complete movement, because in the thesis we also have some equations for the movement in between. So we have then different time steps. So first you simulate, then you calculate, and then simulate again, or?
Yes, I can explain this by maybe we ignore the driver. If there's some question later on, we can come to it. But here you can see the model, and I have an animation how the pulses are in the Thompson coil actuator. So first, the opening coil is energized, and the thing is that in this case the armature is up here, and there will be currents induced and the interaction and whatsoever. And there is this is the point where the force is generated up to the high speed. But the thing is that as soon as the armature travels a bit away from the coil, the thing that happens in the coil actually does not affect the armature anymore, since this is kind of a air core inductor, and the coupling becomes worse. So if you then write down this motion equation of mechanical motion as done in publication 4, you see that all these kind of electromagnetic forces, you can ignore them, and you can solve the simple remaining stuff analytically. And this is when you, let's say this whole process takes 5 milliseconds, then this initial pulse I showed, this is roughly 0.5 milliseconds, so only a fraction. And then you solve this equation of motions, and from this you can get the point just before the armature is next to the closing coil. And then you simulate that process again for the active damping. And by using this kind of approach, you reduce the total time you have to simulate by quite a lot, from 5 milliseconds to approximately 1 millisecond.
Okay, and how long does then the simulation take? So then is it very computational intensive, the whole thing, or?
I would say that I'm not a pro at these kind of FEM simulations. So I think in the beginning my mesh was way too dense, and it took quite a while. And then later on, then I was kind of running into problems because I had to adjust the model and so on. And then I reduced the model somewhat and improved the meshing, that it is still accurate, but not too many details. And I would say then for one run, it simulated maybe 2 hours. But this was already quite detailed mesh, and I would say somebody who, even some of my colleagues I work with, if they would have meshed it, it would have probably taken a couple of minutes for the simulation. And the thing was, though, that here the whole simulation time was relatively long, because we did many simulations for various combinations of parameters. You see in this application, we analyzed the influence of the voltage and the capacitance of the drive circuit and so on. So this was more what contributed to the simulation time in total.
Okay, but there you copied then also the electric circuit with the FEM simulation then in the end.
Yes.
So this was a coupled simulation then. Okay. And one of the results there was that from the simulations point of view, that you said that the decrease voltage should be higher than the acceleration voltage. Am I wrong? That was one of the results of this paper.
I think for the damping voltage, it should be higher than the acceleration voltage.
Exactly, yes, yeah.
And I would say that it is intuitive, kind of, because when you start the process, the armature is essentially right next to the opening coil. So this is the perfect coupling. The damping, however, is initiated when it is still, let's say, 1 millimeter away, which sort of decreases the electromagnetic coupling with the armature, and that's why you should need a higher voltage. However, this is also what the simulation showed, but in the experiments, for some reason, this was not the case in the measurements later on. So it was quite surprising for me why damping was so efficient. But as I also wrote, it was more or less not the goal to optimize this kind of actuator. It was more or less how to apply it in the DC circuit breaker. So that's why I looked into it further.
Because this was also one point where I stumbled on was that first you say, okay, from theory point of view, I would like to have a higher damping voltage than a lower acceleration voltage. And in the real system, you exactly do the opposite of that. It was then
You see that if you look in the graphs in the paper, then you see that it is let's say a difference of 50 volts maybe. It's not very high. And for the experiments, then I said, okay, I have to get something working in the lab fast, so I should make it as simple as possible. And then I said, this 50 volts, this might as well be simulation error. So just fill it with the same voltage. And if there is a bit of contact, maybe it's not harmful. So that was the approach for the laboratory prototype and why I used the same voltage for opening and closing.
Okay. But if one would continue in that direction, this model could be or should then be used to optimize then also the setup of the Thompson coil in the end, together with the driver circuits to make the fastest possible opening. I think that's one step which you didn't do. You made the first initial design study, but then a second step would be then, if you want to continue in this direction, I said to optimize it. And because I think what I understand, you took the setup of the Thompson coil. It's from a device off the shelf from ABB, or I don't know whom.
Yes, it was provided by ABB Corporate Research. So it was I'm also not aware of how they designed it and so on, but you know, it's quite simple in its structure, so easy to apply. And I did not consider how to, for instance, optimize the armature, because this, of course, has a tremendous effect. And you see also in publication 7, there were these kind of big oscillations when the damping was initiated, when the embedded pole was applied. And of course, if one optimizes the actuator with FEM or however one wants to do it, it is possible to get rid of it. So this was not something under my control for this, but one should do it.
Yeah. So in the end, I think it's necessary to combine or design the driver together with the Thompson coil system, and not only independently, if you really would like to get the optimum point of operation in the end. Yeah.
Yes, but one thing that I also wrote in the paper is that the parasitic adaptance in the drive circuit, it should not be underestimated, that it can be a large factor that influences the operation of the Thompson coil actuator. And sometimes one runs these kind of 3D simulations, and the thing that then ruins your lab setup is that you have too long cabling to the supplying source. So that's why one also should not make it more complicated than it should be. And I also found that if you look at the Thompson coil actuator, or this is not maybe one thing that I found, but I have discussed with a colleague, is that the force is actually generated when the armature is very close to a coil. And if you look at it, possibly one could even reduce the models even further, because then one could ignore the motion or neglect it under certain circumstances and consider this in the equations. So I was actually, when I was doing the measurements, I tried to validate these models, and then during this time I also wrote down the equations here and there, and I had some very promising results regarding analytical modeling of Thompson coil actuators. So I think that research could be very beneficial in this regard, since I think maybe Thompson calibrated analytical model could be more suitable than a FEM model in this case.
Mm-hmm. So the kind of a hybrid approach of numeric and analytics combined in an optimal way, and they make it faster. Yeah.
I don't mean faster from a computational point of view. I mean, if you, of course, if you calibrate the FEM model, then it will also be good. But if you can really have a good, fast model that is much more simpler than the FEM model if you calibrate it, and this will still be very close to the measurements.
Yeah. But your FEM model, you didn't compare with any measurements in the end.
There is the appendix of my thesis where I comment on this. And as I wrote, there were some troubles with this validation, especially of the damping, I think it was. I'm not quite sure. But by that time, the prototype was already working. So I did not devote more time to the modeling then, because it was my goal from the beginning to just make the Thompson coil actuator work. If I would have had more time as part of this PhD, then I would have definitely spent some more time on the modeling, improved this, and potentially also on this analytical model I just mentioned.
Okay. And one of the outcomes, what you then presented is new devices and the driver, what you have there on the left-hand side. So they do some energy recovery. Can you comment on how much energy you are really then recovering in the end?
I mean, one has to say that this energy transfer in the Thompson coil actuator is relatively inefficient. So if one discharges these capacitors, only a small fraction is actually dissipated in the armature. And then the energy, of course, has to end up somewhere. And if one uses this configuration that we proposed, let's say this one is discharged by firing the thyristor, then it will be, due to the LC resonance, charged into opposite direction after the resonance. And in our experiments, I think this was roughly, in the absolute value, 55% of the initial voltage. But then you have to consider what is the driving factor for the remaining voltage on the capacitor. It is the losses in the RC circuit, or RLC circuit, sorry. Even though it is the LC circuit, but you have some small r. So if you optimize your design, you can also reduce the r, and then you would have basically much more charge left on the capacitor, some fraction of the losses, but then of course also some share which is burned in the armature. But I have not spent time on optimizing this to see what is the boundary, but I could imagine that it could be well above 80%.
Okay. So much more what you have shown than in the thesis by your measurements, because from one graph I got that it's roughly got 25% of energy left, something like this. But that could be optimized to higher values. Okay. It
is so there are, because in this kind of configuration, the voltage, the current, this capacitor is discharged twice in one operation. And after the first operation, you have a remaining voltage of 55 approximately % of the initial voltage, then just negatively. And then after this process, it is discharged one more time, and then the capacitor is charged in the correct direction or the initial direction again, and then it will be something more like 25. But this is, so to say, after the second interruption, not interruption, operation. Yeah,
exactly. Yeah.
And this figure would then, of course, also be higher if the whole process, if the first process would be 80% instead of 55, then the number would be more like 50% maybe. After this second operation.
Mm-hmm. So the 2 times 80% then would be then 64 or something like this.
Be analyzed in depth.
Yeah, okay. One thing what you then couple by the driver design would be then, because with this operation we have then the losses which define then also the voltage for the damping operation. And that's then related also to the force during damping, and that's also, I think, for a full operation you would be more flexible if this damping voltage could be adapted, or because in the end that's also one problem you had So the full damping voltage was not possible because that was even destroying or causing big problems.
Yes, this was the conventional driver, you mean?
Yes, yes, yes.
Yes, but this, I would say, this is very implementation dependent. And for this prototype, the key aspect was always simplicity. So we wanted to have a vacuum interrupter that we could just apply in the setup, and this used this kind of plastic pull rod. And most likely this is, it could also be the vacuum interrupter, but I think the pull rod could have been a large contributor to these oscillations. And if one would make a product, one would probably replace it by a different kind of connection. So this is one aspect, of course, regarding these oscillations. And the damping, the main motivator for this, why we did not consider this conventional, or why we did not use this conventional circuit, was more or less that it avoided the oscillations because the damping was weaker. So with this kind of novel driver, the damping is somewhat weaker since the second voltage is lower than for the conventional configuration where you have the symmetric voltage.
Exactly, yeah. But that's, you were happy about this because your pole was oscillating in the end. But for if one would like to optimize it in the end, would be more flexible at least to have then also a direct control over the damping voltage. So even go to the other direction, not using the original driver, but one which would have an adaptable damping voltage level.
Yes. Yes, I think it would be good. The advantage of this one is that it has two capacitors less than the conventional configuration. And if you think about, this is what I also mentioned in publication 4, is that from a practical point of view, the drive circuit of the Thompson coil actuator is also a limitation for practical reasons, because you need to recharge the capacitors after the operation. And if you, for instance, want to carry out the auto reclosing, okay, then you can calculate what kind of voltage do you have available in this substation to recharge the capacitors. Is it possible in 300 milliseconds, let's say? And is it possible for two capacitors in this time? The other aspect is this proactive commutation mode. Here you operate the actuator twice within 10 milliseconds. So then it is really questionable how to recharge a capacitor within this time frame. And that's why this driver has a lot of potential for this kind of application, where recharging within a short time would not be feasible with a practical implementation of the DC power supply.
Yeah, you would have to have several supplies or something like this, or several capacitors for the. And with this one, you have then the recharging automatically finished after the action. Yeah.
And possibly one could, if this, in our case now, the damping was not too weak, but as I said, also in the, or as I've written in the publication, we have not pushed the speed of the actuator for these experiments with the embedded pole. Since we both did not want to destroy the embedded pole, and we also did not want to stretch this kind of operation with the proposed driver. The thing is, yes, I think there's still some room for improvement, to say the least.
Yeah. And the operating point, you would then choose a fixed optimized point for the damping in an optimized system, so that you define the damping voltage, the point of triggering for the damping voltage. So that would be independent of the operating point of the DC circuit breaker.
Yes, this system is independent, and also in the lab implementation, these Coil control systems were separated. So we had one FPGA board which controlled the test circuit, and then this control panel, which let's just go back. This had own control system. Takes an eternity. Here it was. No. So this control panel houses all the electronics, and then we have this control electronic boards, which has a simple microprocessor to control the damping. And as I explained, also we have have hard-coded this delay between the acceleration and the damping. We have not used any kind of feedback for reliability reasons. We just tried some sensors to also measure it, like ultrasound and so on, but it was messy, so then we just made it hard-coded. It worked much more reliable.
Okay, and just from my understanding, that the box and also the driver circuit and all the stuff, that's what you have then designed by yourself during the PhD thesis time.
Yes.
Okay, okay. Because for the test setup, what you had, you took parts which have been existing or done in the previous setup, and there you just did modifications, as far as I understood. Or
this structure. This is the test circuit again, and the whole setup. I think, if I'm not mistaken, it was Matthijs who built it. Matthijs Huvelsman, who did a PhD before me, and then he had his setup. He tested some kind of resonant submodules for MMC converters, and then he was finishing. And when I was looking at his topology, I saw that when I was doing the simulations of the test circuit, oh, he also has two semiconductor switches with turn-off capability. He has some thyristors in there and so on. So then I saw that if one sort of flips the topology around, one got to the test circuit. And then Matthijs was so nice to hand me over his prototype. And I took some IGCTs, flipped them around, some diodes, flipped them around, and then I had the test circuit and parts of the DC circuit breaker as well. And there's another thing that is placed behind this thing that is visible, which was taken from a project from Thomas Moder, who's also been a PhD student here. He was also working on submodules, and then I basically used the same approach of using an old setup and flipping around the diodes and IGCTs a bit and made it work.
Okay, okay.
Yes, the inductor is also not visible. This is a big air core inductor, which is outdoors.
Yeah, that's what you mentioned. That it's quite large. Natural convection cooling than outside. Yeah.
I think it has a good foundation, doesn't it? Yes.
Okay. Okay. Maybe coming to this interrupter circuit, where you have proposed in one paper several setups for bidirectional braking or more symmetric operation. And one thing what was a bit open for me there was, because you had quite a list, I think it was 2x3 what you presented there in this paper. What would be the one which you pick and say, okay, that's the best one, that's the one I would use if I need to build some DC circuit breaker setup?
So first of all, I have to mention that this was publication 5 for the people on the stream. And then I also have to say that we later came up with the simplified configuration. And as I wrote in the thesis, some of the topologies suggested in publication 5 are redundant because of this simplification. There are some topologies in publication 5 that are still very interesting. For instance, the ones with the pulse generator that sort of combine the enhanced active resonant circuit breaker with what Professor Marquardt proposed and Yeki Wang. And these, I think, are very interesting because they don't need an auxiliary power supply for the injection circuit. However, my favorite topologies that I like right now, I mean, it's of course a bit not fully objective, but in the thesis, I give some example. Let me see. It is on page 55. So then there in, I'm not sure what the number is in the PDF, but it's page 55 in the printed version. And then you see there that I've in figure 6.11 included 2 DC circuit breakers that use a kind of injection circuit similar to side brakes that builds up the injection currents successively. And this would then also use this LCS assisted triggering for the commutation to the triggered vacuum gap, and then this injection path to get rid of the arc in the triggered vacuum gap. And I think this would be the one I think right now would be very interesting. But I have to say that everything regarding these statements is influenced by the properties of the triggered vacuum gap. And as long as one does not know the properties of the triggered vacuum gap at DIDT and DVDT at after current zero crossing, it is difficult to make a good statement about which topology is more useful, apart from practical aspects such as auxiliary power supplies and so on.
Okay. So because also your measurements all focus more on the low voltage stuff, so that was also would be one question. You also always focus more on the commutation and the low voltage stuff, but all the things happening after the commutation, then you did not look at. So that would be one step what you see as a next step for investigating. So exactly this DI by DT, the DV by DT across the breaker, how this would need to be such that there's no reignition and all the stuff.
Yes, yeah, you're completely right, and this is something that has to be done. The question is this something that one should do as a university research facility, or maybe a company that is interested in such technology? Because the companies, of course, have more resources, maybe also more experience with working with these kind of dangerous high power setups. As PhD student, one is kind of responsible for such a setup. I don't know whether I would have dared to operate my setup up to 10 kiloamps, let's say. So I think this is definitely something that should be done in the future. And I also want to say, for instance, you said that the current levels that we tested, there was a practical reason why we did not test beyond 1.2 kiloamp. It was not the limitation of the DC circuit breaker, but it was the limitation of the test circuit. Because here you need this capacitor as energy source for the test current. However, as I also indicate, we wanted to test this kind of advanced functionality, can it reclose and so on. And if you want to reclose and test this, the capacitor has to be recharged again within a reasonable auto reclosing time. And if one then does the math, one comes up with that 1.2 kiloamp with the kind of power supply that was available to us is the maximum current rating we could test at.
Okay. But there's some limitations also from the university level stuff what you can do compared to what companies could do in the end. And but I think for designing then the whole system, it would be very important in the end to have then a better understanding of the breaker behavior, because especially your circuit of the DCCB is then based or centered very much around this vacuum triggered gap, and without having a detailed understanding, it's very difficult to design it then properly, because in the end it's used in just the black box model, or even don't understand the details. So I think that would be difficult to make a real good system design in the end. There I think it might be helpful. I don't know if it's possible to have a kind of combination of maybe high voltage people could join in, which are a bit more have a better background on this discharge stuff, what is happening in there, on the breakdown. I'm also not an expert in, but I think that's the stuff what is necessary to fully understand then the behavior of such a system, and to optimize then the combination of the power electronics with this breaker in the full system.
I mean, I fully agree with everything you just said. And the aspect is that, as I said, we purchased this device from a manufacturer, and of course they're not going to tell us every detail about it, even though I may have nagged them about it. But the thing is that in the research facilities, one could, for instance, initiate collaborations with institutions that have such a vacuum arc chamber where one can initialize it and study the arc during, for instance, this extinction. And this would be a very interesting thing to do. Of course, one needs the capability to do so. And the other thing, but that is also of concern for me, is that one should have a good discussion about these functionalities, because this also influences a lot. Maybe some of the functionalities discussed are not really needed in the end, or they offer marginal benefits. So this is also a discussion that is very important.
Yeah, yeah. And also for understanding, you have one thing what is mentioned, I think it's in paper 7 then in the end, the latest one.
Yes.
You also had the problem of this, the commutation failure after triggering, so that would be also...
But I think for this, I can just mention that, I mean, we, as part of this research, we wanted to analyze the triggering and the commutation, and we analyze it at low currents. One thing is that we have shown that even though this kind of instability can occur, it can be avoided by dimensioning of the RC circuit. In the paper, there are some more details which also shows that there's a lower bound, or these are the values from the graphs, but we show that one cannot make it too large, but one should not make it too small either for successful operation. And this is one aspect. And the other aspect is that René Smits, who is on the committee, by, I don't know, coincidence, happens to be the author of a paper that investigates the characteristics of vacuum arcs at low current. And there he has already laid out many findings, and I think that they are probably applicable for this kind of application as well, even though the measurement circuit used in that paper differs substantially from the one we used. So I think there is already some knowledge of this actually from the 80s already.
Yeah, I think spark gaps or triggered gaps, I think it's the history is quite long, and sometimes the problem to get the right knowledge or find it in which book it's written or which old paper, yes. Which might be not in IEEE, and then you can't find it via Google. So that's sometimes also a big issue. What we also experienced, that you have to go back in time quite a lot to find the right information. It might have been investigated, but the question is where it is, especially if you come from the outside the field, which is, if you come from power electronics, you then have to deal with triggered gaps. I think this is a bit a special topic, I would say at least. Because it's also astonishing that you have some lower limit for the resistance here, because intuitively I would have expected that, okay, the lower the resistor I make, the better it's triggering, because then the more I'm heating up the plasma and all the stuff. So that there is a lower limit, it's also a bit surprising. Maybe for me, as I said, I'm not an expert on these vacuum gaps, but that's stuff what we have to learn then to design the system properly.
Yes, but one has to say that this, even though this exists, this limit, the breaker, of course, usually should not operate. This is 20 amps, something like that now. Yeah. This is, I think, also one of these kind of critical current ranges of the instability where they occur. And if you just increase it to 30 amps, there will basically be no instabilities anymore. So it is a very narrow current range, and I'm not sure whether it is a true limitation, even though one can, of course, research it.
Yeah. But then one of the main limitations would be to use your breaker system when interrupting or breaking current in normal operation, for example, then this current would be very low. That would be then a critical case, for example, or.
Yes, but I mean, in a HVDC system, even the normal operation level current is 2 kiloamps. So, and then let's say, I don't think that this would be a very big limitation. And especially now it depends on, of course, the application. In the thesis we discuss in the context of HVDC. And for HVDC, then maybe you can use the LCS. And then the simplified configuration, as I stated, completely avoids these instabilities.
Yeah. Okay. Also, looking a bit on time, I think from my side, it would be so far fine, not to make this all too long. As far as I understood, there would be now questions also from the panel side.
Yes, thank you very much. For this very extensive and thorough review of the work by Tim Augustin. It's obvious that you have covered quite a lot during your work as a PhD student. And thank you very much, Jürgen Bieler. Then I would like to turn to the grading committee. And I start in the reverse geographical order, as I usually do. So I would like to invite Professor René Smets. Yes.
Thank you. Please allow me to continue the discussion, or maybe you could call it opposition here, but not after. I would like to congratulate you on the very clear way you have described your work, and I was really impressed by the high interdisciplinary content of your work. But coming to my point, you tested a design at 500 volts, and in your conclusions you state that a full power module can be based on a 55 kV discharge closing switch with a, let's say, a 40.5 kV vacuum interrupter. What do you expect to be the main hurdles in extrapolation of your design by 100 times the voltage and maybe 10 to 20 times the short circuit current? And given the title of your thesis, which reads for HVDC grids, even this 100-time extrapolation seems to be not enough, and stacking of modules seems to be a solution to come to a 1000 times upgrade, which is needed for the HVDC grids, which, for example, are planned in the North Sea at 525 kV. So what do you see as additional complications in stacking modules of, let's say, 50 kV to 10 of these modules to 500 kV, which is ultimately your aim, because you titled your thesis for HVDC grids?
Yes. Thank you first, René, for your comments. And I can go back to this slide, I think, to the ratings. So if you look at these ratings, then let's say you were mentioning this unit, which had a voltage up to 55 kilovolts, which let's say is in the range of the largest vacuum interrupters available, or they're even higher, but which are conventionally applied in medium voltage AC applications. And there are various conventional current injection DCCBs that use vacuum interrupters as interruption medium. And I think that the triggered vacuum gap would probably behave somewhat similar, even though maybe one has to see what is about the triggering of the devices and how the triggering of serious connected devices works. Nonetheless, these stresses that you mentioned, that is mainly the normal operation level, but in the normal operation mode, the breaker is turned on, so there is no voltage across it. It has to absorb the counter voltage during the interruption process. And during this interruption process, one can modularize the breaker, as I've shown on one of the previous slides. And then here, for instance, these boxes in the energy absorption path would be an arrestor each. So during the energy absorption process, the arrestor would define the voltage across each triggered vacuum gap in this case, similar to the conventional current injection DCCBs. The thing is now that what could also happen is that the breaker is in an open state and there is a high voltage on one terminal. And then one would need to assure that there is no dielectric breakdown across it. And I think, as far as I'm aware, for a conventional current injection DCCB, one would use some sort of grading capacitors in parallel to each vacuum interrupter unit, and this is to balance out in case they have uneven stray capacitances. So I think this would be one option for HVDC applications. But this is, of course, all considering that one applies this kind of switch. And as I've also indicated in the results, all our results are just representative for this triggered vacuum gap. If you would use a different kind of discharge closing switch, the properties may be entirely different. Maybe for practical reasons for HVDC, one would not use a modularized structure, and one could use one very large discharge closing switch instead. This is, of course, a design question. This is what we think. It's more a general idea, and we believe that one can make it work.
Yes, if we focus to the switches you use, you mentioned a lot of advantages of the EAR design, But I think one of the disadvantages that 4 different switching devices are being used against 3 in the hybrid design and only 2 in the standard active current injection type. Because one of the switches is a little bit hidden in your work, that is the making switch of the injection circuit. And given the fact that you work with a 500 volt design, you could use a thyristor for that. But once you are going to upgrade your circuit to 50 kV, let alone 500 kV, again, another type of plasma making switch should do the job, which complicates the design even more.
Yes, thank you for your question. I would like to say that the enhanced active resonance circuit breakers are called like that for a reason. They are somewhat similar to the current injection DCCB in that they also use the injections, the triggered vacuum. No, that they use the injection circuit, but they are different because one adds this triggered vacuum gap or whatever. Mm-hmm. So this is, of course, let's say, additional complexity that is added. The thing is, though, that the injection circuit is well known already from the conventional current injection DCCBs. So this would, of course, be taken over. And I think regarding this implementation of the making switch you questioned, one can, of course, see that here it is general. It could be any injection circuit, and it could, for instance, be a solution as Cybreak has used, which does not use a making switch, as far I'm aware of, rated for the full DC link voltage, but only for a fraction of the whole system voltage.
Yes. Okay, I think that were my points. So I think, given to the time, I would like to give the word to the other members of the committee.
Thank you very much, René, for your question and comments to this work. And I would just like to remind the audience that you can also put questions, and you can put them in the Q&A in the webinar, and you can also raise your hand, and I will allow you to talk later on after the grading committee. So then I turn to Professor Elena Lomonova and invite you to put questions to the respondent here. Let's see if Elena is there.
She's muted.
Ah, sorry. Yes, you're muted. Thank you. Good. Thank you.
Yes, I'm here. My apologies. First of all, I would like to also express my compliments about a very nice presentation. And by the way, very nice discussion with the main opponent. It's quite challenging. So my questions will be very short because quite a number of them were already discussed. But I would like to come back to the Thompson actuator, please. And might be the results in the paper which you received. I guess it's the 4th paper. You were discussing that with Professor Bela. So the title of the paper is System Design of Fast Actuator for Vacuum Interrupting DC Applications.
Yes.
When I'm looking at the results of the finite element analysis calculations or simulations, I'm a little bit triggered or puzzled about the correctness of the simulations. Because looking at the scale of the magnetic field density, flux density B, indicates that it is very much saturated, the armature part of the actuator. So it's around 3.5 Tesla.
Yes, but
is it correct in the paper, first of all, or I'm mistaken?
I would say that it is probably correct. The Thompson coil actuator is not like an electrical machine with a iron core which saturates. So it's more similar to an air core inductor.
Okay, but you have the iron part, right? So the armature, is it made
The armature is made out of aluminium.
out of aluminium? Okay, but in principle, under such a flux density, of course, we have to think about, to my opinion, a very effective cooling system, or not?
This operation
Might be, let's convert the question, what is the current density of the coil?
I mean, to be honest, I don't know the current density. The coil is actually relatively small and the current pulse is very high. So in the experiments we ran, in the end, the current pulses were about 15 kiloamps, let's say, of that kind of magnitude. But the current pulse itself will only last 500 microseconds. That's why the coil is not heated up substantially, and that's why it does not need a cooling system. Also considering that the actuator is only operated when the DC circuit breaker operates, which should only occur in a fault case or for some, let's say, rare switching events, and hence there is no sort of losses that heat them up all the time. So that's why I think that this cooling system does not have to be included. However, I have to say that there could be a limitation for auto reclosing operation. We have now shown the results for two consecutive interruption attempts. In some systems, one would expand this and do even further reclosing attempts, and this could heat up the coils. And this is something one should keep in mind. Yes. I hope this answered the question somewhat.
Yes, thank you for the proper explanation, but to my opinion, still the Thompson coil actuator is really a subject of the research on itself. I would not ignore that part on the global analysis. I mean, more thorough analysis. Even you did quite a extensive finite element calculations. Because I suppose it's also open boundary conditions. I do not know how did you formulate the boundary conditions during the finite element analysis?
I'm sorry, I don't remember that. I did the simulations like maybe 3 years ago, so I don't know exactly how to set it up. And I would say that in COMSOL in general, it's kind of intuitive how to set the boundary conditions. Maybe this is this kind of open boundary you just mentioned.
Well, if I'm looking at the problem published in the paper, I do not recognize the explicit formulation of the boundary conditions. Maybe it's just a remark which can be considered as the recommendation. Aluminum armature part, is it a subject also of thermal heat or not?
The heating was not included in the finite element simulation or the cooling. We did not, for instance, calculate the losses and how the armature heats up. We just included the Maxwell equations and this mechanical equation of motion as indicated in this publication.
Would you expect that aluminum armature is also the subject to eddy currents?
The eddy currents are the main operating mechanism of this actuator. So because they set up this magnetic field that pushes the armature away. So of course they have some effect, and the detailed optimization of this Thompson coil actuator was not part of the thesis, but there has been a previous Ph.D. student at KTH who has analyzed this in depth already. And so to say, this is some work, this kind of work we done is based on, and maybe also the designed actuator I received from ABB.
But eddy currents, please correct me if I'm wrong in this case, eddy currents are also the subject of damping, right?
Yes.
So it is included in your analysis as well, or not?
Yes, this is included in the formulated equations that are considered.
Okay. Might be the next one question related again to the couple. By the way, my compliments, because it's very multi-physical problem. It's you have to to be professional in many domains, and I appreciate your way of tackling that. So by no means any criticism, please consider only positive. So you are talking about speed and acceleration. And somewhere, I do not remember, it's in the papers, you told that the circuits, electronic circuits, it's a subject of the very careful tuning for optimizing the performance of the system. What should be optimized, or what should be tuned, and which factors are acting on the or influencing? Let's say, if in terms of weight, if I would apply the brute force optimization criteria.
Of course, this is maybe a good point from you. This is not optimization and calculation with an algorithm as such, where one formulates a goal and then tries to achieve it in the best way. So, and there are also various ways what could be the goal of the optimization. As part of this design, the actuator was given. So there was, for instance, not the optimization of how many turns to use in the coil or how to dimension the armature. This was already given. And hence, the only thing that could be optimized is how to operate this actuator, which is sort of imposed by these drive circuits. And that is why the parameters we played with are the capacitor and the voltage. And we have then not done a optimization calculation where it converges to the optimum, but we have done various simulations for many capacitor and voltage values of this drive circuit to come to an acceptable performance. And if you look in the paper publication 4, then we have also included some of these goals. Let's say the speed should not be more than 3 meters per second and so, as kind of restrictions. But it was not a optimization calculation in a formal manner.
Okay, so it's in kind of your recommendation. Let's call it like this, right?
I would say that we did parameter sweeps calculations of the parameters that we could set on the prototype. And from these parameter sweeps, we tried to extract the more desirable settings.
Okay. When I'm talking about might be your summary of the presentation of the thesis or the PhD work, you are several times telling that the EAR DCCBs perform similar to hybrid DCCBs.
Yes.
But still, what is your preference?
My preference, I think I indicated in the thesis that I actually do not have a preference. I think that the grids that will evolve in the future will not be the same, and the requirement at each node can differ substantially. In some cases, it may be justified to use a cheaper circuit breaker, and in some cases, one may want to have a more complicated circuit breaker that operates faster or that can provide additional functionality such as fault current limitation. And I think that there's also the chance to integrate a lot of the good properties of some circuit breaker in one. For instance, you can see that the enhanced active resonant circuit breakers, they share this injection path with the conventional current injection DCCBs, but they also share this kind of commutation from the main path to the commutation path, similar to hybrid DCCBs. And then there are more concepts that have been proposed by DC circuit breakers by other PhD students, for instance, focusing on getting rid of a component, and all of these could eventually also be considered in a design. So the proposed enhanced active resonant circuit breakers, they are merely just a suggestion to replace these power semiconductors with trigger vacuum gaps. But I think that overall there is still the potential by smart layout and so on to make it even better.
Okay, thank you very much. This ends my questions addressed to you. Thank you.
Thank you very much, Helena, for your questions. And after you, I would like to turn to the sunny coast of Sweden and see if we can have some interesting questions from Professor Torbjörn Thiringer.
Thank you very much, Mats. So first, I would like to say that this was a really amazing presentation. It was really pedagogical, and the energy you showed was really enjoyable. I think the work is really interesting. I think it's a well-written report, and I'm impressed by the experimental work you also done. Although I know that some of the things were prepared for you before. Since I anyway is looking at this summary, did you also have a conclusion slide?
No, I only have a summary slide.
Yeah, but then we can go to page 59 in your thesis.
Should I open it on the laptop as well, or is it okay for the people on the stream?
We see. You can continue first, and then we see how to do it.
If it's a problem, maybe you can read the first. It's on page 59. You have 7 conclusions.
Yes.
And could you read the first sentence just of where your conclusion starts?
HVDC systems, specifically future HVDC grids, have been discussed in the thesis, concluding that DCCBs should be used in ring and meshed HVDC grids.
Yes. Sorry.
Do you want more? Or?
Now you can stop there. When you have a conclusion, what is it you usually have in a conclusion?
I think that maybe my conclusion is more written like a summary, possibly.
Yeah. So I felt a little bit sorry. I mean, you have done such interesting things. And okay, if I come on the next page, I found nice specific findings. But if we start there, I mean, the sentence you read, I think that you could have written without doing the work. And actually, or do you have a comment on that?
I don't agree with the statement. Because,
you don't?
No, I don't, because I specifically also write ring and meshed HVDC grids.
Yeah, but okay.
And let's say as part of this work, we have also done this kind of pre-studies with the HVDC grids, and we have also considered alternative ways of dealing with these DC faults. And so I think it is also important to note that these DCCBs, they are needed in this meshed and ring structure. But for instance, one could also make, there are different approaches. So I think this was the goal of this sentence. Okay.
For me, it felt like if we have a meshed or ring system and we don't want the system to collapse, yes, we need a DC breaker.
But one could think if one could also use it in a ring, in a radial configuration. But this I excluded because I personally think maybe in a radial configuration, a converter-based solution makes more sense.
Yeah, I won't harass you more, but I agree with what you said, that in a conclusion you can perhaps try to be a bit more specific on your findings, especially since I think you have a lot of them. Then I wanted you to jump to page 28, but then maybe I will read it instead.
I can open it on the beamer. I just have to exit the presentation. If that is
but no, don't do that, because I have I will return to the presentation. But if you read the last last sentence in page 28, the last in chapter 4, I was just curious about one thing. It starts with that being said.
Yes, that being said, the complexity of the test scenarios and safety aspects intuitively set an upper limit for test currents and voltages in a university research laboratory. Yes.
Yes. So then I was a bit curious here that it seemed anyway that you did the tests you wanted, but it feels like here you're preparing the author that there were things you couldn't do. So if you elaborate around that, was there something that you where you were lacking current, voltage, ability, or something else?
I mean, it somehow goes in hand what the other, what Jürgen Bieler and also René Smits have asked, that first of all, these currents are very high, and also in the HVDC circuit breaker, which is discussed, the application that is discussed, it is maybe 10 kiloamps fault currents. So this is sort of not something that I say that it is not tested, but I had too much respect for that kind of current level to test it in the laboratory myself, and hence I did not plan the test circuit to provide such currents in the first place. And that is, I think, what I meant by stating this.
Yeah. Do you feel that it's an important sadness, or?
I'm actually not sad. I think that there's a certain thing that one can expect of a PhD student. One can do research, find out novel things, but one cannot expect a PhD student to build a HVDC scaled circuit breaker in the laboratory. I think this is also something one has to accept, and I don't think that it is sort of a limitation. This is something one can leave to the pros, so to say.
Yeah, thank you. Then maybe you can take slide 12. So one thing I was a little bit unclear about here was that once you had come to the simplified configuration, do you see is the originally proposed completely outdated, or are there some drawbacks with the simplified configuration?
I think the thing is about the simplified configuration that it is nice. And it obviously has less components, even though it operates more reliably in the experiments. But it has a disadvantage, or you could say that it has an LCS. And this LCS generates this minimum voltage required by the triggered vacuum gap. If you, for instance, would think about the DC circuit breaker design, where one wants to get rid of the LCS, then one does not have this capability anymore. And then, of course, such a configuration as the originally proposed one could be beneficial. So I think this would be my answer to your question.
Okay, because one thing I was thinking was that you mentioned some problems with instabilities and some in order to ignite the TVG. That there were some instabilities, there were some low current issues. So if you would do this super reliable, so it really could outcompete the reliability of if you have a lot of series connected IGBTs there instead. If you would increase the reliability, what would you do?
Of the original proposed configuration? Or?
Yeah, okay, you can choose any of them. If I understood you correctly now, the originally one was a bit safer if you had low currents.
No, it was quite the opposite.
Was it opposite? Okay.
The simplified configuration can sort of say control the voltage when the triggering in the triggered vacuum gap is initiated. And by this one can completely avoid these instabilities. And the other one, this what I mentioned is that it is highly dependent on the tuning of the RC circuit. And we have also tested this in the presentation. I showed 2 resistor values, but in the corresponding publication, there are several more where we demonstrate this operation. And by tuning this appropriately, one can both avoid these instabilities, and one can still have this kind of initial current for the triggered vacuum gap. So in this case, actually, it's not unreliable. The only thing is that it needs more components than the simplified circuit breaker. But it is kind of obvious that one has a circuit with some passive elements that one has to dimension them and that there's a trade-off and that there may be a combination of parameters that gives a more desirable structure.
Okay, would you go so far? I think you were asked this also earlier, to recommend this solution instead of having a string of IGBTs there.
I mean, I already tried before with my diplomatic statement.
Yes, but I push you once more.
Of course, I'm a bit biased towards my solution since I've been working on it for about 5 years or so. And I think there are clear advantages, but there are also clear disadvantages, and this I cannot sort of hide under the table. Let's say some characteristics that are unknown. But I think that if my expectation is that one could make this a really compact and compact and nice design. So I think it could be better.
Okay.
But considering that one uses this advanced functionality, as I've also said in the thesis, if one does not need this advanced functionality at all, then I would just go with a conventional current injection DC circuit breaker.
Yeah, I realized that you're good in political answers, and that's why you get the new questions on it. You said that you in principle had no voltage drop at all over when the TVG was conducting. Was it? And you said during your presentation that you could have it during a long time. So I was a bit curious. What is a long time, and is it really so that? I mean, some heat dissipation you have to have with all that current.
I think you misunderstood this.
Okay.
The triggered vacuum gap is of course based on an arc discharge, and this arc discharge has a voltage, and this depends on the medium inside. For this triggered vacuum gap, it is a vacuum discharge, and this one has a characteristic voltage of 10 to 20 volts, which then also dissipates energy accordingly. And the second one was, I think, regarding the conduction time. And one can just see that this device had this maximum charge rating. So let's say, even if it has these high current ratings, one can, from these two ratings and the expected worst case current profile, calculate for how long the DC circuit breaker could conduct. But there's a clear limitation. However, if you consider that this is 300 coulombs, if one does the math, then this will amount to a time which is substantially higher an IGBT could conduct breaker current for. So for instance, in the IGBT, you would need to connect maybe units in parallel at some point. And here you can operate it still. And one also has to say that since it's such a simple device, and since this is not made for the DC circuit breaker, the device that is optimized for the DC circuit breaker could conduct even longer. Or higher currents, whatever. I mean, it's part of the optimization.
Okay, thank you for clarifying that. So with this, I'm happy with the answers. So I leave the word back to Mats.
Thank you very much, Torbjörn. Thank you very much to the grading committee and the faculty opponent. We also have audience, and I would like to invite the audience to put questions or remarks. And I know that we have Simon Neer, who would like to put an oral question or remark.
Yes, can you hear me?
Yes, we hear you loud and clear.
Very good. Okay, so first of all, thank you, Tim, for a great presentation, and it's a huge amount of work here that has been done. Very good work. I have 3 questions, so Mats, stop me if I ask too much here. My first question is about the spikes in the measurements. You said that you had we saw some slide where you performed an interruption, and then there was a loss in voltage during the suppression time. Let's see, maybe it was the pre. Okay. There were spikes there, for instance, here, yes. So here at let's say, what could it be, somewhere around 4.7 milliseconds in the left-hand plot, we see that there's a downward spike in the voltage across the breaker and an increase in the current in the injection circuit.
Yes.
So that seems. Do you have a reason? Do you have a? I'm not sure I got this from the question that Jürgen posed earlier. Do you have a good argument for why you think this is noise? Because it seems to fit quite well with that there will be a breakdown in the vacuum switch or possibly in the surge arrestor or somewhere else in the.
But this is the current in the injection circuit, right? This so this is not the current in the triggered vacuum gap.
Yes, but if there's a current there might be a current in the gap as well.
But,
right?
You see here that this current is the one. Oh, you see, there's a small one.
Yeah.
But to be honest, I don't expect this, and I can clearly say why. Because first of all, you know the ratings of these devices, so this is just 1.6 kilovolts. So it is very unexpected if a breakdown should already occur at this kind of voltage. And the other aspect is that we have conducted these experiments before with a solid state breaker when we initially tested the advanced test circuit, and then the same kind of spikes appeared and even more frequently. The
later one is a very good argument. The first one, there are reasons why you might see reignitions or restrikes in a device with high ratings as well, which clear themselves after a very short time. But you saw some spikes before as well. Then have you looked at currents in the surge arresters or maybe in the capacitor in your injection circuit? That there might be dielectric breakdowns there.
Do you mean during this commutation studies or?
No, during you saw the spikes in the suppression time, so possibly there is some component that is excessively stressed, and then there is a breakdown there. Could that be the reason?
I mean, it could be actually that there has been some too high stress on the thyristors in the injection circuit, because this one was destroyed after some time and I had to replace it. So it could also indicate something in there. But I think it's very speculative. But I can say that we had a thyristor failure in the injection circuit after some time.
Okay. Well, it doesn't look like something to be neglected anyway. When it's and then there was a question about the variation of the IDT and the DVDT after current zero in the TVG. Did you have any possibilities to? You have some measure here. So.
No, this is something else. This is just I wanted to click to the TVG slide.
Yeah. Okay. So you had. Did you find some ways to see limits to the interruption capability of this at low current?
At the low current experiments, you say?
Well, this is relatively low currents for HVDC. So, but yes, it might still be interesting with a high frequency interruption capability.
You know that it depends highly on the implementation of the injection circuit.
Yes.
So you will get different outcomes depending on the implementation of this circuit. This is one aspect. And the other aspect is, let's say we just talked the very simple one, pre-charged capacitor and a resistor. Then you will need some components that have to be tuned. And maybe you need a large amount of coils or coil where you can vary the inductance. So in short, we considered this too much of an effort, and is this part of the research activities we have not investigated yet.
Did you do statistics on interruption capability at the points which you could find with variation of current or variation of charging voltage in the injection circuit?
I did not do any statistical studies of this kind of phenomenon. The only thing that I could have evaluated is the instabilities in the commutation studies, since these were kind of stochastic. But let's say the other experiments, everything did not seem to be of a stochastic nature.
Okay, that's very nice to hear. Oh, interesting. So, and then I had a question about the triggering circuit of the RC circuit, RTVG, or it's in this slide as well. The one it's connected to ground. This resistor and capacitor that is supposed to trigger the TVG.
I can leave it here, right? This
Yeah,
one.
yeah. So this circuit, you said that you mentioned that this is modular, but
No, I mentioned that the simplified configuration, where you get rid of the RC circuit, is more easily to modularize, because then essentially you also get rid of the diode, and then you just have the TVG.
could you not get the same behavior of this by just connecting the capacitor to potential B here, and then open the LCS for a short time to charge the RC circuit, and then trigger the TVG, and you would have a bidirectional triggering of the TVG with that circuit.
Can you say it again? I did not get the initial part, or acoustically.
Connect the capacitor to potential B there. So instead of connecting it to ground, connect it to potential B, and then open. When you want to proactively brake, you could open the LCS and charge the RC circuit, and then trigger the TVG, and you would have this pre-charged RC circuit to put the current through the TVG, and I wonder why to connect it to ground and not do it like that.
For instance, just in parallel or something like that.
Yeah, just in parallel.
For some reason, I mean, I must say that this is not part of the thesis, but initially I of course tried to run some simulations of these devices, of these concepts. And as part of these simulations, I used a black box arc model, which was for a SF6 circuit breaker, or corresponding to an SF6 arc, and not to a triggered vacuum gap arc, because I at that point considered high arcing voltages to be worse for the commutation speed and so on. And in these simulations, I also tried various things, how to connect it, but essentially I found that sometimes it did not commutate successfully. Even though I may not be entirely sure why this is the case. But at least this was from these experimental studies a finding that one should have it to ground.
Okay, okay. Well, it seems like you would still prefer the simplified one for a larger scale implementation from what you say now. So
I think yes, this can, I mean, it all depends on the LCS. If you have it, then you can make it work, the simplified configuration. You could also, for instance, use this other technology I mentioned in the review of the DC circuit breakers, this Chinese way with the, I think they call it current commutation module or something like that, which is essentially not placed in the main path, but in the commutation path. So this could be an alternative to the LCS. But overall, if one places some additional devices in the circuitry, one could make it work without this RC circuit. And as I've also mentioned, I've included another circuit in this thesis, which may be close to what you are working with in figure 611. Can you see it?
not yet, but
on page 55, figure 611.
Okay, yes.
So here you can see a configuration with a convert in series with the LC circuit, and then one where the converter is in series with the triggered vacuum gap. And one, of course, this is something I have just thought about in the end of the PhD, but I thought maybe the converter in this case can fulfill the purpose of both building up the injection current, but also for causing for creating voltage in the commutation loop to the main path. So this was one idea which I did not have time to analyze it in simulations or so on, but I think this one would also be interesting. Also considering your background.
Sounds very nice. Yeah. Well, thank you for the very good answers, and yeah, that was all for me.
All right, thank you very much, Simon, for your complimentary questions. I think we've had a really good barbecue party with Tim. He looks a bit tired almost. I'm not sure about that. This concludes the public defense of Tim Augustin. I cannot see any more questions.
I have a question. I have a question.
Oh, Göran.
Yes, yes. Actually, it relates to the same figure. It's figure 6.11 on page 55. I think it's very exciting to see the picture 611B. You have completely got rid of all semiconductors. And I want to know how near we are to that. What are the demands on the mechanical breaker and the converter? So it's exciting to see that we have that solution in some sense. So Tim, what do you say?
So it is related to figure 611B, as I understand, right?
Yes.
So in this case, it's kind of a special thing, and because there's no LCS in the main path anymore, one would absolutely need to use an arcing mechanical switch, which could, for instance, be a vacuum interrupter. And this could be as in current injection DCCBs. And of course, in this kind of commutation process, it has not been studied yet. So I cannot say anything about it, since it should be investigated in future research. In this configuration, the converter, however, is placed in series with the triggered vacuum gap. And this is a disadvantage in the aspect that it always conducts when the triggered vacuum gap conducts, which is somewhat longer than in configuration A. And this converter then has to conduct a relatively high current for a relatively long time. But on the other hand, the IGBTs in Hitachi ABB's hybrid DCCB have also to conduct for the same kind of time. So I assume that it should be feasible. And the converter would then need to conduct this current and build up the injection with the parallel connected LC circuit.
Yeah, and how should the converter be built up? What is inside this box?
I expect that it should be very similar to a Cyrex design. So, but this is still should be researched, since I've not done any simulations on it. I cannot say that it works or anything like that. But I expect that one could, for instance, use a full bridge converter.
Yeah, but with mechanical contact, could it be something else than a vacuum breaker? Could it be a load commutation switch? Maybe an ultra fast such thing? What do you say?
The mechanical switch in this configuration has to be able to at least arc a bit, I would say. But that is up to further investigations. But it has to take some arcing, so a disconnector switch cannot be used. And then when the commutation can be initialized and how long the arc has to burn in the mechanical contact, that is a different question. One could, for instance, try to commutate very early on, just when the metal bridge is forming and when it has exploded, so that one tries to avoid that there is too much of a heat buildup in the contact gap.
Yeah. So I think this figure is quite important, and I think it is actually something that you should have made some recommendation to research on those topologies further after your PhD, because it's so interesting, I would say. So it's just a comment. You should have a more substantial recommendation regarding further work, and maybe you should have that also in the thesis. Otherwise, I think your presentation and your thesis is very good. So that was my questions.
Thank you. Thank you very much, Göran. And I look just for safety that now I do not have any more questions from remote or from local. And that means that I'm going to close this public defense by Tim Augustin on his Ph.D. thesis. On behalf of KTH, I would like to thank the respondent, the faculty opponent, the grading committee, both the remote and the local audience for participating and making this a very successful public defense. Thank you very much, everyone.